Hey guys, welcome to example 3 of 9.3. We're going to be looking at limits of an infinite sequence, and we just need to determine if they converge or diverge. The way we do that is we work with limits. So the question is, if these sequences kept going, do they approach a single number or do they diverge, right? So they either converge to a single value, getting closer and closer to that value, or do they diverge, which, is when they don't approach a single number or they do something else. All right, so let's take a look here. So what happens as for part A, you have 1 over 1, 1 over 2, 1 over 3. You can see that's defined as 1 over n, right? We can write this as a limit. So for A, we'd want to write the limit as n approaches infinity for 1 over n, because that's the explicit definition. And if we say 1 over 1,000 or 1 over 1,000,000, right, we can basically assume that that's going to be approaching 0 and basically 0. Remember my little analogies, you have one piece of cake, you cut it into 1,000,000 pieces and you get one piece. What did you basically get? A 0. And so that's a that converges to 0. All right. Part B, same thing. We're going to look at it as a limit. But over here, notice part B, they don't give you an explicit definition, but it's actually not that hard to figure it out, because if you look at it, again, from a pattern standpoint, you could just see that you have the denominator starts at 1, and then it goes up, and then the numerator does the same thing, but it doesn't start at 1, it starts at 2. So if we want to define this explicitly, we can actually define it as n plus 1 over n, right? So same idea, n plus 1 over n. There's a couple of ways you can do this. Remember, we did this in the earlier chapters with rational functions. So this is not top heavy, it's not bottom heavy, right? If you have a billion plus 1 over a billion, right, that plus 1 doesn't really make a difference. So in that case, you would just say, well, you would just take the coefficients, right, 1 and 1, right, and you'd ignore this 1 over there because it really doesn't matter. And plus, even if there were other variables, remember, you always look at the highest exponent variables, right? And in this case, it's just n to the first, n to the first. So again, this is, they're even, right? They're not, I shouldn't say even, I should say it's not top or bottom heavy. Therefore, just take the coefficients. But you'll see that in calculus, we really want to make sure that we can prove this stuff, because we do know 1 over, not like that. We do know that 1 over n is, as n approaches infinity, we do know that that is 0. So because we accept that, then we can write this. We can split the fraction, so it's really n over n plus 1 over. And actually, let me write it as the limit. Limit as n approaches infinity, n over n plus 1 over n. And in this case, we can see that n over n, it doesn't matter if it's a billion over a billion, right? Infinity over infinity, that is 1. So we're really left with just the limit as n approaches infinity for 1 plus 1 over n. And in that case, now I can see that 1 over n is going to be 0, and so this is just going to equal 1, and again, this converges. For part C, we can see that that's going to just approach infinity, so that's going to diverge. All right. And for D, again, it's going to go -1, 1, -1, 1. That's an oscillation, right? It's like sine and cosine, how the peaks and valleys, it's just going to bounce between two numbers or oscillate in between two values. It can be defined explicitly as -1 to the n, right? So that also diverges because it doesn't converge to a single value as n approaches infinity.